Let's consider the following matrix. We can compute the characteristic polynomial for this matrix simply by computing the determinant of the matrix with 1 minus lambda down the diagonal and 1 everywhere else. If you carry out the cofactor expansion, then you'll come up with negative lambda squared multiplied by lambda minus 3. This matrix has two eigenvalues. They are 0, which has multiplicity 2, and 3, which has multiplicity 1. The proposition tells us that the geometric multiplicity of 0, or the dimension of the eigenspace E0, is bounded between 1 and 2. Since this is an integer, that means it's either 1 or it's 2. The proposition also tells us that the eigenspace E3 has dimension at least as large as 1, but no larger than 1. That tells us it's either 1 or 1, so it must be 1. While this doesn't tell us exactly what line the eigenspace E3 is, it does at least tell us that E3 is a line. To actually compute the eigenspaces, we have to go ahead and compute the null space of the matrices A and A minus 3i. It's easy to see by subtracting the first row from the second and from the third rows that the matrix A is row equivalent to the matrix with E1 in each of its columns. This tells us that the eigenspace E0 is cut out by the equation x plus y plus z is equal to 0. We know that a linear equation in 3 variables defines a plane, and we can see this explicitly by solving this equation for x in terms of y and z. So of course we can express this as the span of the two linearly independent vectors, negative 1, 1, 0, and negative 1, 0, 1. This tells us that the geometric multiplicity of the eigenvalue 0 is 2. Now, if we're interested in finding a basis for R3 consisting of eigenvectors of A, then we'll also want to explicitly write down what the eigenspace E3 is. So we'll take the matrix A minus 3i and row reduce it. This shows us that the eigenspace E3 is the line cut out by the two equations x minus z is 0 and y minus z is 0. Solving these two equations for x in terms of z and y in terms of z tells us that this is the span of the vector 1, 1, 1. So we can see here that we get 3 vectors. So we get a basis for R3 consisting entirely of eigenvectors of A. In this case, the important piece was that we had enough linearly independent eigenvectors. In general, this will happen whenever the algebraic and geometric multiplicities agree. So let A be an n by n matrix. If every eigenvalue has geometric multiplicity equal to its algebraic multiplicity, then Rn has a basis consisting of eigenvectors of A. A particularly nice and oddly common way in which this happens is when the eigenvalues are distinct. If A has n distinct eigenvalues, then Rn has a basis consisting of eigenvectors of A. For example, let's consider the following upper triangular matrix. If we form the matrix A minus lambda I, we'll see that this is also an upper triangular matrix. As a result, the determinant is simply the product of the entries on the diagonal. So we can see here that there are 3 distinct eigenvalues, each having algebraic multiplicity 1. This forces the geometric multiplicity to be 1. So to see this, we can compute the eigenspaces for each of these eigenvalues. When lambda is equal to 1, the matrix A minus I has 0, 1, and 2 down the diagonals and the same off-diagonal entries as A. The reduced row echelon form is then 0, 0, 0, 1, 0, 0, 0, 1, 0. This tells us that E1 is the line cut out by the two equations y equals 0 and z equals 0. That is, the x-axis in R3. We can see that the reduced row echelon form for A minus 2i has entries 1, 0, 0, minus 1, 0, 0, and 0, 1, 0. So we get two equations which cut out the eigenspace E2. They are x minus y is 0, and z is equal to 0. So of course, this will give us the span of the vector 1, 1, 0, which we can see is a line in R3. Finally, when lambda is 3, the matrix A minus 3i is row equivalent to 1, 0, 0, 0, 1, 0, minus 3 halves, minus 2, 0. So this tells us that E3 is cut out by the two equations, x minus 3 halves z is equal to 0, and y minus 2z is equal to 0. Solving each of these two equations, the first for x in terms of z, and the second for y in terms of z, gives us the set of vectors 3 halves z, 2z, z, which of course is the span of 3 halves, 2, and 1. And if we multiply that vector by 2, so that we only have integer entries, we can see that this is the same thing as the span of the vector 3, 4, 2. Now, if we put these three vectors together, we'll see that we get a basis for R3 consisting solely of eigenvectors of A.